Alright guys, this is going to be it's gonna be day 40. Me posting almost every single day until I get job as software engineer. Thank you guys for all the comments and things. Sorry if it's kind of quiet. I am trying to not be too loud because it's like 1 a.m. here. So yeah, this is not gonna be a long video today. I'm just gonna do a little bit of stuff in Go for boot.dev, and then I'm gonna solve a leak code problem because I've been doing that somewhat consistently. So let's get right into it. Thank you guys for all the comments and things. It is really appreciated. One second here.
Wrap the call to get user in a try block because it's a function that might throw an error. For example, maybe the user doesn't exist. And in that case, the catch block runs instead. Now Go does not have try catch blocks. Instead, it just returns errors like it does any other value. If everything goes well, the error is nil. You continue to the next lines of code, just like in this example. If something does go wrong, the error variable, like called error, will not be nil. So we just handle the error, say by printing it and return error. But if everything does go well, then the error will be nil. And it means we just continue to the next lines of code. For example, maybe we want to get a user's profile picture based on their ID. So we call that function that also can return an error. So again, we handle the error either by failing or just continuing. There are no exceptions or throwing, we just have a simple conditional check in this state. So functions that can fail in Go return an error value as their last return value, and we as the caller of the function are just expected to check it. Now there are two main reasons I prefer Go's method of error handling over try catch. The first is it makes a really straightforward control flow. There's no magic that jumps us out of a block that you're in, like the throw keyword does. The code just executes line by line, even when things go wrong. And second, it's explicit. You can see that a function might return an error just by looking at its return type. In JavaScript, the return type does not tell you whether a function might throw an error or not. You just kind of have to know. In Go, you can't ignore potential errors unless you really go out of your way to do so.
Interesting. I don't think there's anything wrong with this, but in general, I have not liked Go syntax, to be honest with you. It's the interface, right? Oh, there we go. Study consistently for 55 days. Can I type B in error and also fill another interface? No. What? How is that the case? Oh, a type can implement any number of interfaces. Interfaces are implicitly type B in error and also fill another interface. Oh yeah, for sure. Yeah. Yeah, it's referring. Okay, that's what it means. Okay, yeah. Okay, that makes sense. Fine. Whatever. There's package that makes it easy to deal with errors. Turns the error that formats as a given text. I guess we have to return y or something. Some value must return as it flows. Error is not new. No dividing by 0. Yeah, it looks like the right solution. Oh, is returned as 0.0. Oh, you're supposed to return to 0 values. So I was supposed to return 0.0 here instead of y. Okay. Cost actions, normal values. Panic function. There's a function that defers or recover. So here we're deferring or recover. They're called panic. Now this new go look at panic recover thing. It's like try catch. I like this. Don't be like them. Basically never, I guess. Logged out fatal apparently. Set their profile status, communicate the current activity to those that choose to read it. However, there's some restrictions on what these statuses can contain. Your task is implement a function that validates a user's status updates. New status cannot be empty. It's greater than 140. Status exceeds 140 characters. That's errors, not new, I think. No, that's not what I'm looking for. Yeah, if error is equal to null. Well, that's if the function is returning error. Then we can check if it errored out. Something has to be returned here, I guess. Status is string. We can't do this, I don't think. And check the error of the function. I don't think we could do that. What's the null value and error statement? Nil. Okay, yes, nil. There we go. Yeah, this wasn't too bad. Okay, well, let me do the leak code question before I get too tired. Saying that I should watch this video on stacks and queues. Yeah, whatever, let's just watch it.
When the movie theater doors open, they don't first serve the person who just hopped into line 5 seconds ago. They serve the person who got in line the very, very beginning, an hour or two ago. And then the next person, the next person. The very first person in is the very first person removed. That's what FIFO means, first in, first out. Now let's look at the code for these data structures. Here's the framework for what our queue class needs. We need this inner class, which is a node, and it just keeps a pointer or a variable that represents the data, and then also each node needs a pointer to the next node. And we gave ourselves a little constructor here. Now when you implement a queue, or when you use a queue, we're going to add things here to the tail and remove from the head. Because we want to add from one side and remove from the other. Okay, and then we need these methods. So let's walk through and actually start implementing these methods. So is empty is very simple. Just return if head is null. If head is null, then the queue is empty, otherwise it's null. Okay, and then peek. Well, what peek is going to do is just return head.data. Now this will throw an exception when head is null. If you want, you can go explicitly check for that exception. Okay, so add and remove are the sort of interesting ones. So with add, what we want to do here is add to the tail. So first thing we need to do is actually go and create this node. Then if tail is not null, let tail's next pointer point over to this node, and then update the tail. Then what we want to do is we want to make sure that there could be a case where the array where the queue is completely empty, in which case head is null. And so if head is null, then this value should head.
Oh yeah, here's
so that's all add has to do.
first in,
Right,
first
now for remove,
out.
we want to remove from the head of the list. So first we need to actually get this head data. Then we want to do is remove the head. So set head equals to head.next, and that basically removes it from the queue. And then we need to say, okay, if head is now null, make sure you set tail to null too, and then go and return that data. So that's the basics of how we implement a queue. Follows pretty logically from the actual design and the algorithms behind it. Now let's look at the stack implementation. Much like with the queue, we have this inner class that is a node class, has a pointer to the next node. Here though, we're going to want to add and remove from the top. So we just need a top, we don't need a head and a tail anymore. And then these are the methods we're going to want to implement. The implementation for is empty is pretty straightforward, just top is null, which is true, essentially. And then I'm going to ignore null pointer checks, which is really simplistic for you all. All peek needs to do is return top data. Okay, so push is the first interesting method. So first, we need to actually create this new node. So new node, data. Then this new node is going to become the top. So node.next is going to point over to the old top. And then the top points over to node. So that's all push needs to do. Now for pop. Well, so pop is when first we're going to want to return the old head's data. So first we need to actually just get that data. So top.data. Then top just be moved and pointed over to the new top, or the next element down. And then we just need to return that data. Pretty straightforward. Now again, I ignored null pointer checks, but if you really want to be complete, you probably want to do some sort of check that says, hey, if top is null, throw an exception, if something like that. That's the basics of how stacks and queues are implemented. They're not too tricky to implement, just a little bit of null pointers and making sure to update those things correctly. So now that you've seen both stacks and queues and the implementation of them, why don't you try these out on a new stack or queue problem? Good luck.
Okay, so this is here Python lists the append method services push and pop with pop. Do not use list with pop 0. Collections.dq. What are they talking about? Is that like some sort of Python function? Oh, I didn't know about this. Okay. I don't know about that. So let's do valid parentheses. I've done this a long time ago. Let's see if I can remember it. So I think we want to do first we need to keep track of everything's like opening closing tag, right? I think we do probably like a hash map or something. Excuse my terrible handwriting. And then we need to like go through every part of the string and add it to a list of some sort. Yeah, I think we had a stack where we added the last one first out, so this will be the last thing in, so it'll be the first thing out. So now we have the quote. I think we need to check if this is still in the stack. I think that's how it works. If its corresponding thing is still in the stack. Then we need to pop again, right? So I think we need to create a hash map with. This is definitely not the right solution. I'm almost positive now. I really don't think there's any way this is the correct solution. And if it isn't, I'm probably just going to look at the solution because I haven't done this one in a long time. I'm almost positive that this is wrong. This is gonna be the stack list for C in, oh, we can't use S. For C in S. Stack dot append C. Then we're gonna say for U in stack. Stack dot pop U if age according to U is in the stack. Pop and pop the stack again. No, if HU in the stack dot pop is current element, then we say if length of stack is equal to 0, then we return true. Otherwise, we return false. This is definitely not correct. Okay, something worked. Okay, so let's print the stack right here and see what happens. So for U in stack, if HU is in stack, pop the current character. Okay, maybe this was correct. And we do need to pop twice. Made really no difference. Wait, what is stack right here? Wait, what if I ran stack.pop here and print the stack right afterward? What do we get back? that seemed to work for, again, some cases. Why is it stopping short? Oh, okay, I don't know, man. I think I'm kind of close, but I'm not entirely sure. Oh. Yeah, stack was correct, but so need something like this in our dictionary. So for C and S, if C and H, so we want to append C to the stack. Yes. And C dot H going to C. I think this would work. So we're checking if, say it's a closing bracket, we're checking if it's in the value of, wait, no, that wouldn't work. You know what, it's too late at night for this. Let's look at the actual solution here. It's been a long time since I've done this problem. Where is it? It's what is it? It's valid.
Hey everyone, welcome back, and let's write some more neat code today. Today let's solve
I don't think I need this explanation today. Okay, yeah, it was. Oh, it's closed. Not open to close. CS of C N H. So he's checking. If stack and stack minus 1. Stack minus 1 is the last element. So we're going through stack and stack minus 1.
An easy problem, valid parentheses. This is such a common interview question. I think I've been asked this so many times. This open bracket, but these do not match each other, right? So these don't cancel out. So this doesn't work. Basically, the order is wrong, and that's pretty self-explanatory by looking at it, right? It just doesn't look right. So now how can we actually determine an algorithm to be able to solve this problem? Well, one of the first things you might notice is we have to start with an opening parenthesis. We can start with this.
Okay, I should feel stack of minus 1. That's the last element stack. You would do. Oh yeah, they're checking the last element is a closing. Is an opening parentheses. Then stack dot pop. Otherwise, just return false. Then the else statement of this is stack dot append C. Okay, so let's what is this? Return true if not stack, else false. So let's go through this. So we're going through each thing as string and we're checking if it is a closed parentheses. It's part of the keys. If it is, then we check if we have a stack, and if the stack minus 1, which would be, minus 1 is actually the first element. Yeah, this is the minus 1 index, this is the 0 index. Good thing I drew this out. We're checking if the minus 1 is equal to an opening. Let's pop. So in this case, they were going through, this is not in the keys. So we would just append it to C. Yeah, we would append it. Same thing for this, we would append as well, because it's not part of the closing. Then here we would check, is this in the list? If it is, then we pop it. This is the -1 element. Since it is in there, we remove it. And then we keep on going through the list. And now we see this. Okay, now it makes sense. Now it makes sense. Okay. That's perfectly fine. It's been a long time since I've done that one, so there's no watch neat code. Call this red, 0 repeats. Use stack hash map for closing things. I don't know what to call it. And then add opens pop when apples stack pop opens from stack when you hit a close. If no open found, turn false. And stack, not empty. Okay, and well, this is technically 8 to 18. So yeah, I have this chart to try and help me keep track and do a whole bunch of repetitions so these problems get easier over time. But yeah, I've been going on for 40 minutes now. Thank you guys for watching. I'll see you all in the next one.